Hi class. Today I want to talk about a little more from Chapter 3. We talked a little bit before about the ancient people and how they developed their understanding of what was going on in the universe, and they had their ideas of things, and for the most part people thought that the Earth was stationary because it certainly didn't feel like it was moving, and there was no indication that there was something called parallax, and so if you look up at the stars, if the Earth were moving around the sun, people expected that you would see these stars sort of at different angles relative to other stars. And so it would look like these stars would be shifting their positions as time went on, as the Earth orbited, if it was orbiting something. And so they said, well, since we can't see that, then the Earth must not be moving, the Earth must be stationary. So we talked about some big names, Aristotle and Ptolemy, and the model that Ptolemy had of the solar system, with the Earth being at the center and everything going around the Earth. So we'll talk about in this little lecture some other people that came along that tried to modify that model and even change it drastically by putting the Earth not in the center anymore, but rather the sun at the center of the solar system. And then we'll talk about some models, some laws of motion that eventually were developed based on observations, very, very good observations that people had made. So Copernicus was somebody who is not the first person to suggest that the Earth was that the Sun was at the center of the solar system. It was suggested before him, but he was one of the first people to really come up with a good model to explain the motions of the planets using a sun-centered model. So he said the sun's at the center, the Earth goes around the sun, all the other planets go around the sun, the moon goes around the Earth. So he had it right, but he used circles. So everything was circular. The orbits of the planets were perfect circles, because he still had this belief, like many did back then, that things in the heavens were perfect. So the sun was a perfect sphere, the planets were perfect spheres, the orbits were perfect circles, everything was circular or spherical, and so on. So he used circles in his model. So it really wasn't any better at predicting future positions of planets than Ptolemy's model, and so people didn't really grab onto it that quickly, because it didn't really do much better of a job at predicting the positions of planets and such. So Copernicus was around 1473 to 1543, and later on we'll kind of just show some dates of all these people and just a little bit about it's kind of interesting in the time at which these events occurred, how much overlap there was between some of these people. So then Tycho Brahe came along, and he was an observational astronomer. He wasn't really a scientist. I mean, he was an observationalist. He was somebody who made really, really good measurements of the stars. Still the best measurements that have ever been made with the naked eye. He did not have telescopes, but he had devices that he could point at objects in the sky and measure angles very precisely. So he made these measurements of positions of planets and stars over the course of many years, and his data was excellent. But he wasn't a really strong mathematician. He knew some math, of course, and so he developed his own model of the solar system. He said that, yeah, the Earth is at the center of the solar system, but he did realize that there are some differences. He did realize that it's going to help a little bit to fit his data, his observations, if some of the planets did go around the sun. So he had the Earth at the center with the sun going around the Earth and some planets actually going around the sun. So he didn't have everything going around the Earth. And that model, it was okay. It still didn't make great predictions of things. But again, he wasn't a good mathematician, so he needed some help taking his data and really fitting it to his model, trying to prove that his observations of the positions of these planets matched what his model said they must be. So he hired Johannes Kepler, to do this. Kepler was a mathematician, a brilliant mathematician at the time, and he was able to take these numbers, this data that Tycho had made, and try to fit it to a model. Now, just think about how hard this is. This is before calculus. This is basic trigonometry, basic geometry, algebra, and while he had this set of data, hundreds upon hundreds of angle measurements between planets and stars and such over the years, and he was able to show three laws that the planets sort of obey as they orbit the sun. He was able to show that the observational data is best fit with a model that has the sun at the center of the solar system and the planets going around the sun, not in circular orbits, but rather in elliptical orbits. And I mean, this is just imagine how hard this would be to do. You're taking these measurements from a moving platform, the Earth, and you're measuring the positions of other moving objects. To take all that data, not knowing that you're on a moving object, the Earth, and to show that that all implies that you are on a moving object. That's it just is it, to me at least, it sounds really difficult. So I've always been very impressed with how he did this and the fact that he did do this in the first place. So Kepler came up with these three laws of planetary motion, and again, he's basing these on Tycho's observations. These are not laws that we can derive. We don't know, Kepler didn't know why these laws were true. He just saw that this is what the data suggested. This is what Tycho's observations suggested. So his first law is that planets go around the sun in an ellipse rather than a circle. A circle is actually a special case of an ellipse. So here we have a circle, and the circle is, you can draw a circle if you put a little tack in your paper and tie a string from that tack to your pencil and just keep the pencil at the same distance from the center. That's a circle. There's one central point. Well, an ellipse is where there's sort of like 2 points that you nail down your string. If you put your string, imagine taking your string and just making it a loop of string, and you just nail down 2 points on your paper, give them a name, call them, each point is a focus, so together they're referred to as the foci of the ellipse. And you take that piece of string and you put your pencil in there and you kind of just make it tight so that it's nice and taut everywhere. And you let your string, you just kind of move your pencil around so that the string remains tight. You'll trace out an ellipse. So that's a particular shape. It has a particular mathematical equation for it. And again, a circle is a special case. If these two foci came together to the center right there, then you'd have a circle. All right, but an ellipse is a little more general. And you can have different eccentricities of ellipses. So the circle has 0 eccentricity. This sort of medium ellipse has sort of moderate eccentricity. But you can have something that's highly eccentric, where it's more egg-shaped, sort of more oval-shaped, where the foci get closer and closer and closer to the actual ellipse. So things like comets orbit in very eccentric elliptical orbits. Planets, though, most planets, except maybe Pluto, most planets have almost circular orbits. The orbits are almost circular, not perfect. So there's a little animation on the in the study area of Mastering Astronomy, and if we go there, we go. Here it is. We can show. You just pick 2 points, call each point a focus, and then you tie a string from one focus to your pencil to the other focus, and you just let your pencil go around, keeping that string tight. So this just plays as you draw your pencil around like that, you get a nice ellipse. And you could change this. This little animation doesn't let you do that. But if you change the focus, if you were able to do that in this animation, you could draw other ellipses and just see how changing the focal points changes the shape of the ellipse, the eccentricity of the ellipse. So that's Kepler's first law, that we have elliptical orbits. Here's another picture. Now, we said there's these two foci. The sun is at one of the foci, at one focus, and there's nothing at the other one. It's just empty space. And so Kepler didn't know why this was true. He just realized that from the data, this must be true. The planets do not go around in circles. They go around in these elliptical orbits, and the sun is is at one of these foci, and there's nothing at the other one. And then his second law, he realized, through his observations again, he saw that as the planet gets closer to the sun, it actually speeds up. And as it gets further from the sun, it slows down. Again, he didn't know why, but this is just an observation that he made. And what we'll talk about later is that this is due to something called conservation of angular momentum. All right, in order for the planet to have this thing called angular momentum be constant, not changing, it must be true that if you get closer to the sun, you have to travel faster. And it also has to do with energy conservation as well. So that's something we'll get to later. But this is an observation that Kepler made. Again, he didn't know physics. Newton hadn't come along yet to describe the laws of motion. But he came up with these sort of these laws of planetary motion, planetary orbits, based on simple observations. We'd call them empirical laws based on observation. So the planets travel faster when they're closer to the sun. The closest point would be over here. It's called the perihelion. So that's a good word to remember. Perihelion is the closest point in a planet's orbit, or any object's orbit really. The aphelion is the farthest point. So perihelion and aphelion. And then his third law was a more mathematical law. He was able to actually look at what's called the period of the orbits of planets, the time that it takes to go around once. And he was able to show that the time it takes to go around once, if you square that, if you multiply it by itself, and you express it in years, so for the Earth it would be 1 year. If you square it, multiply it by itself, you get the same thing as if you took the average distance of the planet from the sun and multiplied it by itself 3 times, cubed it. So if you express that in astronomical units, AU. So the Earth has a period of 1 year, so this number would be 1 squared, and it has an average distance of 1 astronomical unit, so this would be 1 cubed. And yeah, 1 squared does equal 1 cubed. But there are other planets. Mars, for example, has a different period. If you square that, you get the same value as if you took the average distance from the sun to Mars and multiplied it by itself 3 times. So this is a more mathematical law that he derived from Tycho's observations. So here's a way of kind of plotting that. If we have a graph and we plot on the vertical axis the square of the period of the various planets, and there's a bunch of planets sort of in here that have very small orbital periods, and then you get to the outer planets that have bigger orbital periods, and these are just the visible planets that we can see with our naked eye. So there'd be Mercury, Venus, Earth, Mars down in here, and then Jupiter and Saturn. Uranus and Neptune you can't see with your naked eye, nor can you see Pluto. So Kepler didn't know about those planets. So if you plotted that anyway, a period squared and average distance cubed, you get a nice straight line. There's a direct proportionality between them. So looking at this little exploded area here where you can see the innermost planets, Mars, for example, has a period in here. This would be about 3.5. This would be squared, so about 3.5 would be the square of the period of Mars, and that's equal to about 3.5 astronomical units cubed. So if you actually looked up in a data table those actual distances, you can see that relationship and how it holds. But just remember that relationship is for if you express the period in years and the average distance in astronomical units, then you get the period squared is equal to the average distance cubed. This is another way to plot something. What you can also do is you can think about the speed of the planets, the average speed of the planets. Now we said that with an elliptical orbit, planets change their speed. They get faster as they get closer and they're slower as they get further away. But there's some average speed of the planets. On average, how fast does it go? And when you plot that in terms of the distance, you see this nice decreasing graph where planets that are closer move faster, planets that are further away move slower. And this is a very common feature of a gravitational system, a system where gravity is causing things to orbit. And later on we'll talk about this, and we mentioned this a little bit in Chapter 1, where when we look at galaxies, we see that this pattern doesn't really hold. If you look further out in a galaxy, you see that the speed actually kind of stops changing for a while. It doesn't decrease. And so that is an indication that there's something else going on, that there's some other mass contributing to the motion of the stars around the center of a galaxy. And that's something we call dark matter. And astronomers have somewhat of a handle on what that is, but there's still a lot of questions about what it is. They haven't really confirmed yet what this dark matter is, but there must be something else besides just the mass of the various stars that you see. So here's a little question. This is just something you can think about. This equation shouldn't be too intimidating. So here we say we've got an asteroid. It orbits the sun. So not a planet, but an asteroid. But it doesn't matter. Whatever orbits the sun should follow this relationship, that the period squared equals the average distance cubed. So it has an average distance of 4 astronomical units. How long does it take to orbit the sun? Well, if you just take 4 and multiply by itself 3 times. So 4 times 4 is 16. And times another 4, 16 times 4 then would be 64. Alright, so 64 should be the square of the period. So take the square root of 64. You should get 8. Yep, should get 8. So 8 years would be the orbital period of the asteroid. And so astronomers do this. They measure distances to asteroids or they measure times, and they're able to calculate the other quantity, whatever it is they're not able to measure directly. So again, Copernicus came up with this model of the sun-centered solar system. Kepler verified it through Tycho's data, but modified it and said that the orbits were ellipses. But there were still a lot of people that had problems with this. Still, there were a lot of people that believed that the heavens were perfect, and so the orbit should be circles, and this idea of everything above the Earth being perfect and the Earth being stationary was really a very solid thing in people's minds. They didn't have a lot of reasons to think otherwise. So, part of science is to say, okay, well, let's just do some experiments and see whether this is true or not. So Galileo was one of the first people to really do experiments, to make more detailed observations of nature, of a lot of things. Actually, he was more involved. He wasn't just involved in astronomy; he was involved in all kinds of things. He said that he addressed these 3 points. At least there's others as well. Some people said that the Earth could not be moving because the natural state of things was to be at rest, and so if the Earth were moving and you threw something in the air, that thing would want to come to rest, and so the Earth would leave it behind. It would fall backwards in a sense if it was deep, if it was sort of removed from the surface of the Earth, and so if because we can throw things up in the air and they come right back down to us, people thought that must mean the Earth doesn't move. Again, because if the Earth moved, then if you threw something up and it was no longer directly connected to the Earth would sort of leave it behind, and it would appear to kind of fall in a particular direction rather than straight back down. So Galileo addressed that question. He also addressed the question of this idea of perfect circles in the heavens, spheres and circles and so on like that. And he also addressed the question as to why we could have the Earth orbiting the sun and still not see parallax with stars. So again, we don't see stellar parallax because, well, they didn't know why. But the idea is that if the Earth were moving, we should see the stars shifting their positions amongst one another as the Earth moves around the sun, if the Earth were moving. And so since people didn't see that, they concluded the Earth doesn't move. So he did a bunch of experiments. Galileo did a bunch of experiments with objects falling from things, and he realized that no, it's not the natural state of objects to be at rest, but rather the natural state is for objects to stay in motion unless there's some force that acts on them. This was sort of formalized as Newton's first law of motion. Galileo was really the first person to sort of come up with this. There isn't an equation behind it. It just simply says that the natural state of an object is to move with a constant velocity, speed and direction, and it'll change its speed and direction if a force acts on it. So if you think about now, okay, I throw an object up in the air. Well, if the Earth is moving, that object is already moving with the Earth. And so if you throw it up in the air, it'll just continue to move with the Earth unless something pushes on it in some other direction. So you push on it to throw it up in the air, but you're pushing straight upward. You're not pushing left or right. So it's not going to move left or right. It's only going to move up and then come back down because it's moving right along with the Earth. So that was one way that Galileo addressed that objection from way back from Aristotle's time. He also looked at the moon, and he saw that the moon has a bunch of craters, pits, and mountains and stuff. So the moon isn't perfect. It has imperfections. He also saw sunspots on the sun. So again, imperfections on the sun. So this idea that things up in the heavens are perfect, attained less and less validity as he made more and more observations with a basic telescope at the time. Galileo didn't invent the telescope, but he did make one of the first reflecting telescopes, and he improved upon the refracting telescope. And then about the stellar parallax issue, Galileo, again using his telescope, concluded that stars must really be a lot further away than Tycho thought. In fact, he looked at this band of light that people saw across the sky, the Milky Way, and he saw that it wasn't just this cloudy band of light, it was actually individual stars. And so the stars must be really far away. And so if they are really far away, then even if the Earth does move around the sun, because the stars are so far away, it's going to be really hard to see the stars shifting their positions amongst one another because of that different perspective that we'd have in different positions in our orbit. So that was a way of saying, no, we can still have the Earth move and still not see stellar parallax. The reason is because the stars are just really far away, and it's just simply hard to measure that. So this is one other thing he saw people objected about things orbiting the Earth. He said that people said that everything must orbit the Earth. But what he showed when he looked at Jupiter is he showed that other objects could orbit other things. That's not, there's no problem there. We could have moons orbiting Jupiter. So he discovered these 4 bright moons of Jupiter, which we now call the Galilean moons of Jupiter. And then he looked at Venus. He looked at the planet Venus, and he saw, if you look carefully at Venus over time, you see that Venus goes through a cycle of phases just like the moon does. It has a full phase, it has a new phase. So this is what we see of Venus. If we think of Venus then, if you think about the Earth being stationary and the sun going around the Earth and Venus going around the Earth, then possibly you can come up with a model where you get some phases of Venus. So when we see Venus kind of in this orientation, either in line with the Earth here, the Earth and the Sun here, or here, we see a new Venus, but we'll never see a full Venus. You'll never see a Venus that is fully illuminated in this model. And people didn't have, around Ptolemy's time, people didn't have telescopes to be able to see these different phases of Venus. So Galileo used the telescope to look at Venus and realize that sometimes you can see crescents of Venus, sometimes you can see gibbous phases of Venus, sometimes you can see full phases of Venus, and this is only possible if Venus is going around the Sun, rather than Venus going around some epicycle between the Earth and the Sun. So Venus, the observations say that Venus must be going around the Sun to be able to see these different phases of Venus. So a little summary of the dates. That you don't need to memorize these dates, but it's a good idea just to have kind of a sense of where these people were in history and how they overlapped. And so Copernicus was born in the 1400s, 1473 to 1543, and he didn't overlap Tycho. Tycho was born a couple years later and died in 1601. Kepler, of course, was alive during Tycho's time. Kepler, worked on Tycho's data, and Galileo was alive during that time as well. Galileo was alive during both Tycho's and Kepler's time. So, it's very possible that these 3 individuals might have talked, might have known each other, possibly. And then Newton. It's interesting, Newton was born the year that Galileo died. And so we'll talk a lot more about Newton in the next lecture. So again, in summary, Copernicus created a sun-centered model, and Tycho provided data that we needed to improve the model. The model is sun-centered, but with elliptical orbits. And then Kepler came up with his 3 laws of planetary motion. The orbits of the planets are ellipses rather than circles. As a planet moves, as it gets closer to the sun, it sweeps out this area in equal time. So if it's closer to the sun, it has to sweep out this area, and it has to do it sort of faster. It has to move faster to sweep out the area. And if it's further away, it doesn't have to move as fast. So this is sort of a geometric argument that Kepler came up with using his data. And then the 3rd law was this more calculation-based law based on period and the average distance from the sun. The square of the period is equal to the cube of the average distance. And then Galileo made all those different observations we talked about to really overcome a lot of the objections that people still had about the idea of the sun not being in the center of the universe. And so our current model today is basically this, that the planets go around the sun in elliptical orbits. And as we'll see, Newton came along and he was able to come up with some laws of physics, some physical laws of motion, and really explain why Kepler's laws are correct. And then, even later on, Einstein came along and talked about gravity and thinking about gravity in a different way, and he improved further upon the Newtonian view of gravity. So we see, this progression in science is that we get improvements and improvements and improvements on our models of nature and how it works. And people are always challenging things and questioning things, and that's good. That's always part of science. You always want to be questioning. So people continue to question even after Kepler and Galileo and Newton, and people are still questioning to this day. And that's what science is all about. So have a good afternoon, and again, always email me if you have any questions.